Okay, thank you, Shai. So some of you may have heard this talk already in the Bootstrap conference or a similar talk, but we thought it is appropriate for the subject of the workshop. Also, I haven't given this talk with slides before, so it's probably going to go faster than I think. So please feel free to ask as many questions as you have. So I'm going to talk about, this is based on this paper that came out in the beginning of the summer and work with all of these people. So I'm going to talk about the bootstrapping the statistical Ising model on the lattice. So this is the action. It's just an infinite sum. So I'm talking about an infinite lattice at finite spacing. Specifically, I'll talk about cubic lattices and in 3D and square lattices in 2D. So let's see, I'm restricting to J positive. And without loss of generality, there's a symmetry that takes H to minus H. I'm going to talk about the positive H, just to simplify the presentation. Okay. So the methodology is the same methodology that has been, or a similar methodology to the one that has been employed in a few papers before. So first, this is not about the methodology. This is just maybe an important paper in setting up the way of thinking. So the loop equations, which are maybe the analog of what I will call spin flip equations, my equations of motion, were derived by Migdal in '83, but really the methodology that I'm going to talk about today started or at least in our community, started its way in a paper from 2016 by Anderson and Kurczynski, where they essentially took the loop equation in pure Young-Mills and kind of set them up in a way that looks like a bootstrap problem. Henry Lin was inspired by that, and in 2020 he wrote a paper about matrix bootstrap. And then in 2022, Kazakov and Zheng took Anderson and Kurczynski's work and using a technique of relaxation made it more feasible. So Anderson and Kurczynski had some nonlinear constraints. Some of the constraints were nonlinear, and using relaxation, Kazakov and Zheng made the constraints linear and hence made the numerics tractable. So this is a very short kind of introduction to what comes before our paper. But if you don't know this, you can just, I will explain all of the methodology that we used from, you can think of it as an introduction to this. So also I have to mention Han in 2020 used a similar approach for quantum many-body systems. And actually, even before these papers, Gulowski in the math literature used a very similar approach for a classical limit of Hamiltonian systems to constrain the classical limit. So again, the model is just the Ising model on the lattice, and our observables are sets of spins, correlators of sets of spins. So they are. This is quite a literal expression for what one would hope to compute. And this notation here, S underline A, just means that this is some set of spins. So it's just defined as the product of spins as at a different position as x1 to xk, which are defined to be the set A. So this is an example for such a set A, locations on the lattice, positions on the lattice. So the expected phase diagram for such a lattice model looks more or less looks like this. Here we have a critical point where we have the Ising CFT that all of you know very well. This is the H and J plane, so H and J. And after the critical point, we have here a first order phase transition. So we'll have a spontaneous magnetization on this line. Now, here in the vicinity of the critical point, well, I drew it as a finite vicinity because I don't know how to draw an infinitesimal vicinity, but this is a scaling limit. We have the Ising field theory, which is the non-trivial field theory you get by starting from the Ising CFT and deforming by a generic combination of the two relevant operators that you have. So what I'm going to talk about today is our work where we explore this plane, putting rigorous bounds on both the expectation value of a single spin and the expectation value of two x and y here are neighboring, so two neighboring spins. So how do we do this? What are the constraints that we input into the STP solver? So first of all, we have what we call spin flip equations. So these are essentially Schwinger Dyson equations. They are equations of motion. They are in other theories sometimes called loop equations. They are essentially what you get if you observe this expression here, and you change the variable of one of these spins. So I just flip it. I call 1 - 1 and 1 - 1 1. I will show more details later, but these linear relations these will be linear relations between different sets of spins on the lattice, the expectation values of different sets of spins on the lattice. And the second constraint that we have is the positivity conditions. So many of you know reflection positivity in Euclidean QFTs. So in this context, reflection positivity will be very similar, but on the lattice. So also I will give the more explicit expressions, but this is the one we use the most. On the lattice, we also have something called square positivity, and we have also specifically for these theory something we call Griffith inequalities. I will also talk about them. So essentially, this is all of the constraints that we put in, and I will show you the bounds that we get on observables of the theory. I think I'm going extremely fast, but okay. So the spin flip equations. We start with this expression for the observable. We choose one site z, and we change variables in the sum. If z is not a part of the set A, so we start here with some specific observable, and then we choose a site z. So it's a choice of observable and a site. And if it's not in a site A, we get this type of equation. You can see it by just changing variable here. And of course, if it is a site, if it is one of the sites in A, then we'll also get an overall minus sign. So you can see already here, this looks like generically, if this wasn't a spin variable that can take values at 1 and -1, this would look like an infinite sum of observables. But you can see it actually involves only 5 sites. So this is the site z, and these are the 4 sites that are neighboring to z. So in the exponent, we only have these 5 sites. So if we expand it, because every site can take inside the sum the value +1 or -1, this has to be some finite sum of these. So the algebra, if anyone is interested, you can look at the paper. It's not extremely illuminating, but this has to be a finite sum of observables.
So you're always flip only one spin.
We only flip only one spin, because if we want to flip a few, it's just it will be equivalent to including the constraints coming from flipping one spin for different configurations.
One interesting property of this, one interesting concept of this construction is the existence of null operators.
Yes. You're saying even already at this level, you're thinking about this. So here, the null operators at this level.
Like think about this as A, but suppose we just flip the spin to the middle with left spin.
Yes.
Saying that this flipping the spin basically means equivalent to inserting the C to the minus to J whatever, like 4 spins. So that thing inserted over 4 spins is basically equivalent to the unit operator. Everyone else.
Yes. Yes.
So it means that if you take the difference between that guy and the unit operator, then it's null operator. It's an operator which is not real one. The zero correlation function with everyone else.
Yes, that's true. Yeah, I'm not sure. I mean, this is essentially just the equation of motion. So you could think about this in just Yeah, I agree though. We have also we find also other null operators in this construction that maybe are even more non-trivial. I can say something about this later, but yes, I agree. You could think about it this way.
Is it gonna have a proper interpretation of non-predictor? I mean, you should be able to have it when you have more uncertainty. Yeah, well, not the interpretation of the null operator. Well, something like null, uncertainty, like notion of null. It's just an operator which focuses on trivial interpretation. But it's only trivial when you pair it with a single state operator. So it's always trivial as long as all other insertions.
Essentially, not inside this. Okay. Yeah. We will talk about some proper null states later. Okay, thank you. Yes. So this is an example of some spin flip equation. So we could, I think this is what you get if you start in 3D. So this is a cubic lattice, and you start with the A being the empty set, sorry. And we put Z in the origin, and we get this constraint A4 and B. A and B here are some functions of J. This is at age equals 0, and this is a very maybe not so intuitive constraint that one gets. This has to vanish. So what do we do in practice? I will talk about this after in more detail after I introduce the positivity constraints. But in practice, we choose finite subsets of the lattice, and we keep only. So this would, in principle, give us infinitely many. You can start with any A, any infinitely complicated A. So you get infinitely many constraints on an infinite lattice. But what we do is we truncate to some finite subset of the lattice, and then we keep only the constraints that are completely included within the lattice. So this is a rigorous truncation because we only throw out some of the constraints, but we don't modify the constraints that we keep.
Sorry. So these are linear constraints?
Yes.
And so you mentioned in your earlier slide that there's a similar setup of being null and for null.
Right. Maybe I can comment on this. Yes. So in Young-Mills, you also naively get linear constraints, but then if you want to utilize large N, you have factorization, which relates some variables. For example, a variable which represent the expectation value of two loops factorizes to the product of two variables. So if you want to use large N factorization, you lose linearity, but what you gain is that you have a lot less variables, because you can relate a lot of the variables, a lot of the naive variables that are disconnected loops are actually related to more basic variables. Yeah, I mean, a priori, you could try to do the setup in large N Young-Mills where you keep all of the variables independent and you don't use large N factorization, but I believe that would be much weaker. Here, we were surprised that everything just worked out without large N. So we have a lot more variables. The number of variables grows very quickly. So I think even someone was working on finite N at some point. Finite N Young-Mills, trying to do this without factorization, just this approach. So I said we consider, so in 2D we use this tiny diamond and then this bigger diamond. So here we have less constraints. Once we go to the bigger diamonds, we have more constraints. This is like the truncation that we choose, and we can see the bounds improving. The reason that we choose this type of diamonds is exactly the form of the variables that are included in the loop equation. So if I think about the loop equation involving the origin, as long as my original A was within this smaller diamond, my eventual correlator will be within this diamond. And the same is true for the bigger diamond, as long as the site I choose for the spin flip is one of the smaller diamond sites. In 3 dimensions, we wanted to do the same. So we started with 1, 5, 1, we call it. So this we call 1, 3, 1. This we call 1, 3, 5, 3, 1. So we started with 1, 5, 1. And then we were supposed to go to 1, 5, 13, 5, 1. But that was, let's say it's possible that it's tractable numerically, but it was beyond our reach for this work. So what we did, we took this type of region where it's 1, 5, 5, 5, 1. Eventually, that was the biggest region we considered. And the numerics certainly don't improve at the same rate when you do that, because you're including a lot less spin flip equations. So reflection positivity. On the lattice, we have 3 reflections that keep the form of the lattice on a let's say a square lattice. One of them is a reflection on the side, horizontal or vertical. Another is vertical or horizontal reflection right between the sides, and the third one is a reflection on the diagonal reflection on the sides. If you try to do a diagonal reflection off the sides, you will see that it doesn't keep the form of the lattice. So of course, some simple algebra can prove that these are the only 3, but I'll ask you to believe me. And these 2 are easier to argue for intuitively, because I could say that I have some I have an inner product interpretation. I can think about this half space, integrating out this half space as creating some wave function of this I guess wave function of these sides, and this will be its conjugate. So this is an inner product. I think this one and this one. The middle one is easier.
But I don't know what one is the last one.
Oh, okay.
Okay, no. Yeah, I agree.
Yeah, because the variables here live on where we cut it. So, yeah, essentially all of them can be proved by simple algebraic manipulation. But in terms of intuition, I think these 2 are, yeah. Yeah, and for this one, you can just expand the cut links. You cut it and you expand in the cut links, and you get infinitely many terms, but all of them are positive. So the positivity is manifest. And explicitly, the meaning of this positivity is that for any variable constructed out of a linear combination of spins inserted only on 1/2 of the space, I have this condition where R is the corresponding reflection. So this gives me a semi-definite positive matrix condition on my variables.
It's just different because the left and the diagonal, they are positive even for negative change.
Yes. Yes, thank you. That's a good point. That this one isn't.
You just trying to put it out.
Thank you. I appreciate it. I think I am maybe going. Yeah. Okay. Right. If one wants to repeat this exercise for -j, it could be you would lose some of the positivity, but not all of it. So in principle, it's possible. Someone told me that he does Monte Carlo and he cares about antiferromagnets, but maybe someone will do it at some point.
Are there other kinds of lattices for which you are having better constraints, the honeycomb lattices?
I don't think you will gain, at least naively, I don't see what you will gain from this, but from going to a honeycomb. But I'm not saying that. I haven't thought about this. I think you will get a similar set of constraints. Yeah, too hard for me. Yeah, I mean, it is true that on a honeycomb, you might imagine that maybe the regions you can choose for and have as many spin flip equations as you can are.
If you want to go and check the first limit, you can choose the triangle lattice.
Yeah.
This one is the largest symmetry goes into foundation.
So there are more positivity constraints. Square positivity is this weird lattice positivity where you can take any operator. This is not on a half plane. This is just any operator on the any combination of spin variables on the lattice, and you just square it, and it has to be positive because this is just a finite. This is just an infinite sum of positive quantities. Yeah, this is just a result of the action being real, essentially. I think in QFT we are not used to these type of things because when we try to square an operator, it's not such a naive, operation. Essentially, we need to worry about what is the definition even if the squared operator is. But here it's clear what we mean by squared operator. So. But numerically, we find that this is redundant because this is just an experimental observation that any bound that we found, we try to add square positivity in addition to reflection positivity, and it did not improve any of the bounds, not in any way that we could observe. The last positivity is very specific to positive J and very specific to this model. And it's called Griffith inequalities. I think the first place that it was derived is some book by Jaffe, but maybe there are papers where it appears before. This is an infinite set, or at least a big set of inequalities. Actually, I'm not sure if there are a finite number of them or infinite number. I don't remember. But the first two are these constraints. So first, all of the this is for positive age as well. If we flip age, there's some trivial restatement of this. So all of the expectation values are positive. That's first. And second, we have that, this constraint, that the expectation value of two sets of spins, or if we break up an expectation value of some big set of spins into two sets, we get something smaller. This also tells us that if we think about taking a derivative of the action with respect to J or H, this also tells us that our expectation values have to behave in a monotonic way. But this is not a semi-definite positive constraint. It's actually, I think it's even not convex. So it's very hard to work with numerically, at least in the methods that we know. Okay, this is just what I said, I guess. So when we solve the spin flip equations, what I'm calling here primitive subsets is you take all possible spin insertions on the lattice and you mod out by the lattice symmetry group. So this leaves you with a big set of primitive variables. This is the region that I'm talking about, dimensionality, and whether age is well, here I mean age positive, a positive or zero. So a priori, taking into account also the H2 minus H symmetry, for this case, we have, for all of these cases, you can see that we have a lot of primitive subsets of variables. And after taking into account the spin flip equations, we get a much smaller set. So in practice, what we do, we take these big primitive subsets, we write down all of the spin flip equations. It's I don't remember how many. It's thousands and thousands of equations for each one of these cases. They are highly redundant, and we solve them numerically, but to high precision, and we just plug in the solution. And then we write down the positivity constraints that we want and put this into an SDP. So we write down the positivity constraints already in the terms of this smaller number of variables. So the hope is that the bounds will converge. You will see that we have good evidence for that. And the question is how fast. Oh. That's a good question. Well, you can choose any 19. Yeah, I think you can. So, for example, for the age equals 0 case, we restrict either to the even number of spins or odd number of spin insertions. So for the this I think is for the even number of spin insertions. For the odd number to be slightly different, just because of that form of the region that we choose, the numbers. But I think there is no problem choosing 2 adjacent spins to be one of your variables. I don't I don't remember off the top of my head. I assume that if you just think about 2 or 3 simple, that one's not separated, the one separated by 1 side, they shouldn't be linearly dependent. Maybe you can add one separated by 2 sides. I don't have any insight about the form of the, but if you're interested, I can try to look at them. But I right now I don't have any insight to share about the form of these variables. Let's see. Yeah, and the other question is how fast these bounds will converge. So before I show you some of our results, I will talk about some subtleties about the implementation. So if you, if you want to implement this, you will also encounter this type of subtleties. So first of all, we have a very large number of spin flip equations. So we cannot solve them analytically in J. We have to plug in the value of J we want and solve numerically. And the first thing you might want to do is just do this in Mathematica. Okay, some of us are willing to not write code in Julia or Python. Some of us are willing to wait half a day and let Mathematica run. But actually what we found is not only is it much slower on Mathematica, also these the algorithms that are used become very unstable numerically once you have a very, very large set of equations, and involving some of them are also involving some separations of scales when J is in some certain set of values. So we use, instead of that, a QR decomposition. We use some QR decomposition algorithm that Julia has. If anyone is interested in the details, I can look later and remind myself. But and only after the QR decomposition you take the R. So right, you have Q orthogonal and L upper triangle. L upper triangular. Yeah, I think, okay. Yeah, this is L. I think I meant to write R, upper triangular. But yeah, I think that's a typo. But I'm sorry? Oh, I'm sorry. Yes, the positivity, the set of linear constraints that are the loop equations. The spin flip equations. So you can write the spin flip equation as this big matrix. It's not a square matrix, and you would like to essentially use a Gram-Schmidt or something to get the eigenvectors of this matrix, sorry, to get the solutions to this matrix. And I'm just saying that the way we did this to get the numerical stability, we had to use some fancier QR decomposition in Julia. And then only then diagonalize this R that you get from the QR decomposition. So for example, for this configuration, that was the biggest configuration that we considered, you have to compare half a day and 50 digits accuracy that Mathematica needed to perform this, to solve the loop equations, to 16-digit accuracy that you needed in Julia, and 90 seconds of running. So this really became oh, it's just the numerical algorithms that we found and tried to use were not stable enough. So that's just. I think generally in terms of efficiency, Julia is usually superior, but in this case, it's very significant. It's possible that you can find a clever way to do this in Mathematica and I don't know, avoid some of these problems. But yeah, I mean, Yeah. I'm not sure. Yeah. Yeah. Anyway, yeah, the actual implementation was done by Ing specifically out of us. So if I can ask any questions that you are interested in, but yeah. Oh, sorry. So all of these spin flip equations, no, they're not linear. You have a lot of them. You have thousands of them, as you can see, they reduce your variables only by a few hundred numbers. So it's very hard to solve. We found it hard to solve them numerically. Yeah.
Maybe the way of seeing which is the biggest effect. It's kind of a similar question to Bootstrap, like
I mean, you could try to, if you already know these numbers, you could try to truncate their sets of equation in some way and try to see whether you manage to get enough of them to reduce the number of variables appropriately. I don't remember thinking about this. Yeah, that's definitely possible.
No. Wait a second. I thought he's saying he's now applying this on the.
I'm sorry, applying this.
What you're talking about is after you have the independent ones.
No. I'm talking about the spin. I'm talking about this going from here to here. Yeah. No, but you could imagine that you would have a good way to guess. Let's say, I don't know. Here I have what do I have? 550 independent ones. So maybe you have a good way to guess 500 of them. That's what I thought you meant. And then maybe you give up 50. But actually, reducing the number of variables is quite important for the numerics. So yeah. So the second challenge that we had is that we have a large scale separation in the data. Here I'm already talking after I reduce them, and I'm writing down the positivity matrices, the semi-definite positive matrices in terms of the variables I'm left with. For example, in terms of these 19 variables, these matrices in terms of the numbers have large scale separations within them. So they might have 10 digits difference between two entries of these matrices. That would be a typical scale separation. So of course, we have the usual tools that are sometimes even implemented within the SDP of rescaling the variables and rescaling the overall matrices. But this we found does not really help much with the scale separation, which seems to be inherent. So you effectively lose about 10 digits of accuracy when working with these matrices. And so we used two SDP solvers. One of them is Mosaic that works at machine precision, so a double precision. And we use that wherever 5 or 6 digits was enough. So whenever we saw that the bounds are not converging very well, for example, so you only need 2 or 3 digits to resolve the upper bound and lower bound, we can use Mosaic. And Mosaic was much faster and efficient and modern than SDPA. And whenever we could, and whenever we need more precision, and you will see in the results that in some cases we can resolve the max and mean bounds to 16 digits. So obviously we need more precision than Mosaic. We used SDPA quadruple double. So yes.
The bottleneck is in finding the linear independent equations, or is it in solving equations?
Finding the linearly independent ones, I would say. Yeah. Okay, so we have 2 steps here. This relates, maybe I wasn't super clear here. So this is, here I'm talking about solving the spin flip equations, which is the first step that we do exactly. And here I'm talking about using the SDP for solving, for finding the minimum and maximum values for some correlator given some set of semi-definite positive matrices. So here in this first step, the bottleneck is, I would say, yes, extracting a minimal subset of linearly independent, sorry, a maximal subset of linearly independent equations. But this one, generally, the SDP solver is the bottleneck in the bigger picture. So solving the spin flip equations is typically less of a bottleneck than doing the SDP. Well, it depends what we want to do. So 15551. Oh, in this case here, yeah, here it's 90 seconds if you do it right. Although we eventually wanted more than 16-digit accuracy, so it was a bit longer. But let's say for 16-digit accuracy, this is 90 seconds, and this, yeah, this I think for this case was not even tractable. We had to truncate the positivity matrices and run it for a few days. So yeah, this is a much, yeah. But actually, if you want to go back and ask what can we do for example, 1.5.13.5.1, you could imagine that here we could still truncate the positivity matrices. So we have some way to deal with. So I'm a bit jumping ahead here, but we saw that truncating the positivity matrices in some random way didn't harm the numeric so much. So this is something we can do here. But here we have nothing to do. So if we have 1.5.13.5.1, I think we didn't manage to solve this, and there is no giving up constraints that we can consistently. Well, as Shai said, I mean, or Shai didn't say, but as I understood Shai wrongly, I could give up some of the spin flip equations, just have more variables. I guess this is something we can try, but it will just make this step harder.
Experience know that SDP algorithms they look like linearly independent stuff. Linearly independent stuff.
That's right. That's true. That's fair. That's a good point. Yes. Yeah. Right. Yeah. That's true. Actually, we had issues with it. So thank you. That's right. So we really have to. Yeah, but okay. So maybe saying it. Yeah, I guess. Okay. So this is the SDP problem that we have. We want to minimize some generic expectation value. In practice, it will be the ones I mentioned in the beginning, subject to the constraints that we wrote before. So yeah. So let's talk about the results. Unless anyone has any questions before. Okay. So first I will talk about 2D Ising at zero magnetic field. So this is of course a solvable model, but still we can compare it to the numerics we get just to see how well we do. So as I said before, in 2D we used two regions. One was the 131 and one was the 13531. So this corresponds to the gray dots and the blue dots. This is the max bound. This is the min bound. Same here. And we can see that are close to criticality. This line is the critical line, the critical point in J. Close to criticality, our bounds are a bit looser, but far away from criticality, they become very good. We can, for example, compare them to Monte Carlo. So I would say so here, this is a very naive Monte Carlo that we did ourselves. Specifically, Joshua Sander did this. And this is a 10 to the 4 sweeps. This is 10 to the 6 sweeps. We see that if we wait much longer, this will slowly go down. This is a log plot. So the error will slowly go down. This is an estimated error with 1 sigma. And the blue line is the difference between the exact result that we know to our mean bound, lower bound, and the green line is the difference between the exact result and the upper bound. So you can think about our error bar as being essentially this McDonald's sign here. And you see we don't really beat Monte Carlo, but we come pretty close to that in some regions that are far from criticality. And essentially sometimes our mean bounds, or I guess sometimes the in our usual language, the exact result saturate one of the bounds are much closer to one of the bounds than the Monte Carlo result. Okay. Another thing we might want to look at for a zero magnetic field is the spontaneous magnetization. So this is the expectation value of just a single spin. Here, the mean bound is always 0. And we only have the max bound. So the max bound we get, so these gray dots are 1, 3, 1. The red dots are 1, 3, 5, 3, 1. And the crosses are what happens when we don't only use reflection positivity, we also use the first Griffith inequality that I mentioned before. So we just input that all of the expectation values are positive. Okay, that's the extra thing. And you can see that this pushes the max bound here to 0 much earlier. So here, sorry, maybe I should explain what you're seeing. So you see the orange ones, the 1, 3, 1 plus first Griffith are equal to are essentially equivalent to the without Griffith inequality until some value of j, and then it pushes down the max value, the max bound to 0. So we really here can well.
The max bound to 0, exactly 0.
Sorry, yes, to very, very small numerical values.
What is on the y?
It's just positive.
Yeah.
Yes, I saying 0 is misleading to very, very small numerical values. And you can see that the same thing happens for the 1, 3, 5, 3, 1. So we see that here the Griffith inequality is important for the for constraining the one spin.
There's no way for you to impose like decimal in the field, so you know.
That's a good question. You want right? It doesn't know if we're above or below the cut. I agree. Actually, we will talk about what we get at some small positive age. So yeah, I think yeah, I will show what we get for small positive age. Okay, so now if we want to take some positive age, we can plot here. This is you can see a j age plot. The value is the height of this thing. This is the value of this thing is the Monte Carlo value for this correlator, and the color just tells us the distance between the mean and max bound. So we have the essentially the value of the correlator and the error bar according to the bootstrap that we are doing. So you can, if this plot maybe is a bit more readable because maybe the value is not so not such an intuitive thing to think about. This plot is a bit more readable. Here we just have essentially the error bar that we get from our bootstrap approach. And you see that for 0 age, the error bar is not great, as we actually saw before when we compared to Monte Carlo. But as we take age large, for some reason, I guess probably the reason is that the correlation length decreases faster than here, when we took j small or large, and we get at some regions even 10 to the minus 15 gap between the mean and max bounds. So we really nail down the value of the correlator to accuracy of 10 to the minus 15. We have here this feature that I think some of us discussed before. We believe that it's probably related to some scale coming from false vacuum bubbles. If you think about the field theory that lives here, yeah, maybe this is a bit too much of a speculation, but it should correspond to some emergent scale in this theory. Let's see, what can I say? So So yeah, you can see that really when with our method is very, very, very good when the correlation length is not very large, which is not exactly the region we care about physically, but it is what it is. So here I just to again stress how fast this method becomes accurate when the correlation length becomes small. This is Monte Carlo as we change age. Here I'm just sitting on the critical value of J, and I'm varying age, and you can see that Monte Carlo improves very slowly, and at least for Monte Carlo that we did at least. While our error bar improves to, this is again a log scale, so it improves very, very fast. Yeah. This is just to show that the two are in agreement up to, I think it was 2 sigma. Okay, this is another set of results. So here I'm fixing age to be some positive value of age, and I'm varying J. I'm looking at the 2-point correlators and the 1-point correlator. So the blue dots are the upper and lower bounds we get from our 13531. First of all, maybe something I didn't say and should be kind of clear from these plots, the improvement we get between the 131 to the 13531 is very, very significant. So this gives us optimism to believe that if we manage to go further, 135.731, etc., very quickly we will get better and better bounds, even in regions that the bounds are maybe not very tight. So here what you can see is that as we increase J, we have some non-monotonic behavior here of the mean bound, and of course that cannot be some physical feature. So we know that if we extrapolate, essentially, if we take a straight line from here and up to, let's say up to here, then this triangle is essentially ruled out by the second Griffith inequality. So essentially the minimal plot we can make that is monotonic is the actual bound we have, and I will show you soon that if we that indeed these dots violate the second Griffith inequality. But also you can see, maybe related to what Slava was asking before, if we take h to be smaller, so at 0.03, if we look at the 1-point function, we see that our lower bound jumps to 0 at some value of j. So of course, as we improve you can see that here it jumps to 0 very quickly. Here it's a bit better. So as we improve the numerics, we should be able to push this up. But then when we try to take h to 0, again, it is being pushed down. I guess indeed, as you said, this is because we don't know how to. I guess at h equals 0, we don't know how to tell the numerics that we are above or below the first order phase transition. Let me see, anyway, you can see that our bounds are very, very close to the value for h equals 0.3. Well, that's exactly that's I guess the same lesson that I was saying before. So here, this is a plot that's supposed to show you the significance of the second Griffith inequality for these cases. So if we look at the 1 and 2-point functions at this is also at age, some positive age. We see that sorry.
There's a problem. I think you're the only one who.
Yeah. Okay, let me get back to this because okay. So let me just say that in 3D we have this is the result at zero magnetic field. So this is the 151, 1551, and 15551. You see that the improvement is not as significant as we saw in 2D because we cannot increase the region at the same in the same way that we do in 2D. But still, these results are pretty good, far away from the critical value. Oh, I'm sorry. The red line is a Monte Carlo result. And you can see that it's interpolated not very beautifully, but it's an interpolated Monte Carlo result. Yeah. So here, let me just.
Significance of G1 or G2?
This is the significance of G2. So. Yeah. We are comparing G1 and without G1, but the orange dots are essentially where where G2 is violated. So you can see that when you get a non-monotonic behavior, it's exactly where G2 is violated. So we cannot implement G2 because we don't know how to write it in terms of a semi-definite positive condition. But we can see that the points where it's violated are exactly these orange points. We essentially found the result and then checked G2. And you can see that the orange results are where it is violated. Sorry, the orange circles are where it's violated. You can see that when you include G1, it's either orange or blue. So we chose to do it blue where G2 is not violated, orange where G2 is violated. Yeah, it's a nonlinear constraint. I can. Did I skip too much? Yeah, this is G2. So it's a nonlinear constraint. I mean, for special cases, for example, well, obviously when A is equal to B. Impose it after the fact. So, for example, you can impose a monotonicity after the fact, but that's maybe not that's probably weaker than what you will get if you include all of the constraints that this implies. Of course, you can impose monotonicity after the fact. Oh, you just plot it, and then after the fact, plot the minimal function that is above your function is monotonic. I mean a very naive thing to do, but.
The plot of
I'm sorry.
Was a lower bound.
So the plot that you mean the one, this one? Yeah. I think it's yeah. This is a lower bound. Yes.
So it could only go up if you correctly implement G2.
Exactly. If you include a G2, it could only go up. So I guess in this case you could just continue a straight line from here, or continue a straight line from here, because you know that cannot be below that. But that's just a very naive thing you can do. Was I going too fast? We know that the parts of G2 that we can include as a semi-definite positive condition are not enough to impose this, are a bit weak. The non-trivial ones, the interesting ones, are actually I guess, yeah, you have to find some fancy relaxation way to include them. The standard relaxation also will not work because of the non-convexity of this condition. So yeah, essentially, if you try to draw a three-dimensional thing where you have SA, SB, and SA, SB, it looks kind of like, well, I'm not good at drawing, but it's something like this. So usually a linear relaxation would just force it into something linear, but then it becomes trivial. So it's hard to perform relaxation here. but we haven't really tried hard. We just looked at it and thought, okay, this is hard. Maybe someone can do better. How am I doing on? Oh, okay. Okay, so I'll just summarize maybe. So in terms of future directions, there are two questions that we are mostly interested in. One of them is, how do we probe the field theory? How do we get to the continuum? How do we get to long correlation length? And it's hard to see how to do this from this approach purely, but one could hope to combine this with some approach where you are trying to do block spin transformations and think about the RG flow. So you think about the RG flow, you use these bootstrap constraints to relate essentially your maybe your expectation value before and after the RG transformation, or maybe, well, this is very early days, so we're thinking about this right now. And another thing we're thinking about, maybe even for even on the lattice, it's interesting to find alternatives to Monte Carlo when you have chiral fermions, theta angle, complex chemical potential, or any other physical setup where you have a sign problem with Monte Carlo. So that so in these cases, you might find that it's a bit. You might find sometimes that you don't have the positivity that you need to do this, but in a lot of cases, it seems, at least from analysis that we did so far, that sometimes there is a positivity even in cases when there is the sign problem. So these are not how they say, they are not the same, having a sign problem and not having positivity. So it could be. I would say we are also in this direction. It's early, but it seems like there is no reason why one should not, at least in principle, be able to set up this bootstrap problem. Yeah, I would say these are the two main things we're thinking about. And this, of course, is interesting also in the context of the Young-Mills theory that Kazakov and other people were working on. Okay, I have no more slides.
Any questions?
I'm sorry.
I mean, how does the computational cost grow with the net choose? You need to first choose a region of spins, right?
Yeah. So the computational cost grows pretty quickly. That's essentially the problem here.
But quickly is like polynomially or exponentially?
Oh, I haven't thought about this, but maybe yeah, I can tell you. Let me think about this. I can tell you how long it took me to do took us to do what we did, I guess, and you can tell me if it's. Maybe we talk about this later. I haven't thought about the classification in terms of this.
Just going one step higher, but something you try to just immediately prohibitive with the experiment, right? Just going one step further, bigger diamonds.
Let's say you're thinking about, say, 2D. So 2D, we did 13531. Right. 1357531 seemed possible for us with our. It seemed like it should be possible, but that we need to be smart. For example, truncate the positivity matrices, be very smart about the algorithms we choose to solve the spin flip equations, but it seemed possible. Yeah, I'm sorry, I don't have a more rigorous answer to this. We can think about this. I'm happy to. We should know this. I agree. It's just. I think the important thing is that the bounds here are rigorous. So wherever they get close enough, you are just happy. You don't need to think about this. Yeah. So, but I agree. If you want to get very reliable results close to criticality, it's not clear that you will get them without being a bit smarter about, for example, thinking maybe I need. So one thing we thought would be useful, but turned out to be not so useful, is to say, okay, let's consider only. Instead of just truncating to a region, let's also truncate how many spins we insert in our correlators. But that it seemed that we need to go up to half of the spin that you could possibly insert in a region, which is comparable in terms of number of variables. So we didn't really. This wasn't the correct way of being smart about this, but I agree. We need to be. That's why we are also thinking about RG because it seems like just using directly this approach will not get you very far if you want to continue. Thank you.
Yeah, further questions?
Probably really stupid, but would there be some useful connection between the fuzzy sphere and
Oh,
Yes.
yes. Yeah, I'm not sure. I think I missed your talk, so I will listen to the recording and then we can talk about this.
Yeah, so a question of my own, I guess we've discussed before is
Yeah. Good question. We wanted to discuss this, but we never got to it. So our variables will be like this, like lines that end up on fundamental and anti-fundamental. I don't remember what we discussed. Yeah. Good question. I think it might make it a bit harder, the fact that it's not closed loops, but
So obviously solving the sign problem will be very significant. If you have any sort of concrete ideas about a fermion equation model that you would want to first attack with this?
For now, we were looking at staggered fermions.
Staggered fermions, what 2D is?
Into the 2D. So it seems for now that the number of variables is a bit large for this. But if you have ideas of other examples where we would have less variables.
Is there like
so I'm not an expert on this, but if you, you're thinking the same model, just lattice implementation that goes to the same thing in the. I actually don't know. Yeah. Yeah, I'm not sure.
Because many fermionic models, the reflection speed is very sensitive. Arc-adjunctive.
Yeah, maybe we should talk to him.
Another question is, you had this truncation to a finite region, but it was not clear to me if the system of equations allow some sensible truncations which would cover infinite large regions. Could you?
Yeah, I can't. I mean, you could infinitely large regions. Yeah, probably the answer is no. I mean, I mean, now I'm trying to think about this. I'm saying, okay, maybe I truncate to some finite number of spin and add some cost for the spins to be far. So the further they are from each other, I'm allowed to have less and less spins or something like. But this is not really infinite region, right? Because at some point I'm telling you you're allowed to have 0 spins. So, I mean, you could also think about 2 regions like this and take them further apart. The problem will not know what the distance is between them, but still. Yeah.
But some of the constraints you're imposing are equal to the constraints. Because it's not restricted.
Yeah.
And yet you are restricted to the binary region of the point.
Right. So actually, something we realized a bit too late, just very recently, is that actually our constraints are also exactly the same on a torus of on a torus with even number of sites.
Yeah.
So actually, all of these are, yeah. So I guess physically, the implication of this is that the correlators for a torus of even number of sites are very close wherever our bounds are good. The correlators are very, very close to the correlators in the infinite lattice. But I agree, this is a problem. But maybe this gives us a way of thinking, okay, how do we rule out this torus, and then maybe we can improve our bounds where, yeah. But this is something we realized, I think, because what we did to just make sure that we are ruling out the finite torus, we did the sum for a 5x5 torus. And check that it is that it violates the bounds that we got for some values of J and H. We just explicitly did the sum. But the funny thing is that there's something about an odd torus with odd number of sites. So for a torus with odd number of sites, you don't have the diagonal reflection. You have to have an even number of sites. I can draw some pictures if people are interested later, but the idea is just that when you do a diagonal reflection on torus, there are two lines that you can think of the reflection as being across, and if the torus has odd number of sites, I mean, then the second line will be in the middle between sites, and we won't be, yes. So this is very, very scary. But if anyone wants me to draw the pictures, I can draw them later. So this is kind of a funny observation. So this is like our bounds are either for the infinite lattice or for the 6x6 torus for now, for example, in 2D. I guess I'm thinking just about 2D. 3D,
8 by 8.
Also 8x8, 10x10. Yeah. If we increase the region, it will be just 8x8 and 10. Yeah. Yeah, I actually promised to say something about null states. So if you think about this reflection positivity, the saturation when you, yeah, maybe I don't know if I have time.
Oh, you have done it.
Okay, so if you think about the reflection positivity matrices, when we are minimizing one of the variables, we are essentially going to values for our solution. Our solution to the minimization problem is such that we develop. This is something we observe, and maybe one could expect. We develop eigenvectors with 0 eigenvalue, or a very small numerical eigenvalue that is very close to 0 as we go to places where our bounds are very close. The mean and max bounds are very close. So we find eigenvectors with very small eigenvalues for these positivity matrices, and that corresponds in the cases where your positivity is. For example, in this case, this corresponds to the insert each one of them. If you insert this eigenvector is a linear combination of spin variables, and if you insert them on this half space, you will get a null state here. Essentially, that's what this. Well, let me see. What is the correct statement? Yeah, if you insert, there is a certain non-trivial linear combination of spin variables. If you insert them just on this half space, the state that you will get on this interface will be a null state. So, and these are not implied by the spin flip equations because we already implemented exactly numerically the spin flip equations. So these are really some more non-trivial dynamical null states. And currently, we think this is just related to an OPE. It's like an appearance of the OPE out of the dynamics, where we have, the OPE is this type of relation that we could seem on the half space as some null state, but actually it's just expanding one operator in terms of other operators. In 1D, it's very obvious why we'll get them, right? Because in 1D or Hilbert space on a point is, I mean, this is a 1D lattice. I didn't really talk about the results for 1D lattice because they are trivial, but too trivial. But in 1D, it's very clear why you will have such null states. Well, in quotation marks null states, because there are many spin configurations you can think of in the half space, but there are just this is just a two-dimensional Hilbert space here. So yeah, so we are still trying to understand these null states. Our hope is that that will be another avenue to improving the numerics if we can understand their origin and how to find them faster than by solving the this positivity STP problem.
Okay, so let's thank the speaker.